Hey everyone, welcome back to my channel EduVibe. Today we will start with another topic of forces and fields, which is the motion between the charged parallel plates. We are introducing about the parallel plates in the previous lesson. We do one question related to this and how the parallel plates are doing, and now we are learning more about these parallel plates, how the motion between the charged parallel plates going. Like this, we have positive, we have negative, we have connected to the volt, which is again your potential energy. We have to discuss in this, and but now we have to discuss in like another aspect where we consider the electric field now in this again. So we have the more one formula for electric field again, so which we have to introduce today. So okay, so charged parallel plates. So as you learn the formula, the equation of calculate the electric field strength around the point charge. So what is that formula? You do the electric field is equal to kq upon r square. So this is the formula we have done. But to determine the electric field strength with the parallel plates, we go back to the general equation of the starting point, where we do a starting equation. As I told you, when we do one equation like this one, and from here, I told you that this equation is not like doing for that concept. We are not doing that one, but for now we have to consider that one. From there, we can find that what's the original value of this. We are not worried about any derivation of this, how can the formula make, but the formula can be made by like long derivation. But we will just know from here, like these two formulas interacted to each other. When we do a derivation of some part, we get the formula of electric field is equal to delta V upon delta T. So the delta V upon delta T is the formula we have to know. That delta V is your electric potential difference between the place, which is going to be by volt, and this is in meters. This is the distance between the place, the separation distance, like in this, the separation distance, this one is your this one, and the electric field you have know this is in V per meter now. So as I told you that we have Newton per coulombs or we have volt per meter, you get this from that, the volt per meter from that form. So question for this. So this is the easy type of questions as we do in the previous lessons. We do same thing in this, but with the electric field and the potential energy, both aspects we are going to each other. So determine the potential difference experienced by a proton undergoing the motion shown below. So we have a proton over there, they are going the motion in the parallel plates. So here we have the potential difference. This is delta V in this that is, and this is the separation distance. And we have to first use the formula to get over to this. Basically, we're trying to delta V experienced by proton undergoing a motion, but we don't know that how they go from this. So for this, we use this formula two times in this, but in different aspects. But firstly, we have to find the electric field in this. So delta V is 80 volts. Your delta D is this, that 1.2, and I remain M and M because I will tell you that why because it cuts out. So when we calculate this, you get 66.6 is repeating volt M and M. So this is your electric field, but now you want delta V. For that electric field, you have to find for delta V. So you have to again use that formula. Now you want delta V. So electric field times delta D. So this is 6.6 is repeating V about M multiply by delta D. Delta D is your, now you have to visit this delta D. So this delta D you have to consider, and this will be multiplied by 0.70. This is mm, and when they multiply, so that mm cancel with that. So when they cancel out, you get delta V of 46.6 is repeating volt, which is 47. So in that question, you use that formula twice, which we have given to us when first we do with this and to find the electric field. Because in that case, when we do this, that case we have electric field in constant. But when they motion, when they go in motion, protons go in a motion, that electric field not in like We have to find that particular electric field or that thing. So that electric field you have to use in this. So then you have to find that delta V. Delta D is different from inside to outside. So outside distance we have to calculate first, and then we go to inside to find out what's going on in this. So that's how the question works. We will do more questions. You get more understanding of this topic. Why use the two formula twice in the same question? So this question is again a very important question. There's different aspect in this. So we have to find the minimum work required to move the alpha particle as shown. So we have the diagram. So as I told you, first we have to do outside one. Like we have the separation distance. This is D, delta D, and we have this, which is delta V. So from here you can find the electric field. So delta V is 600 volts. Delta D is 12 centimeters, but we wanted this meters. So this meters should be 0.20. So 0.12 meters. So when you solve this, you get about 5,000 volt meters. So we get that formula. We find the voltage. We want that voltage which is equal to delta EP. From here, the charge and delta V. You want a delta V. So again, you can use the same formula. Delta V is equal to now E upon delta D. Because you want this, so you multiply both. So this is 5,000 voltmeter. Delta D. Now what delta D you have to use? This is the horizontal. This is like horizontal one, but you want that one. The vertical. Like we do it this, we get that one, vertical one. The horizontal one we use when we do the perpendicular aspect. I'll discuss later on. But we use this. So this part, so this one has to be cut over that. Yes. We use just this one. So this is 8.0 centimeters, which is 0.080 meters. So when you calculate this, you get about delta V of 400. So this is 400 volt. For alpha particle, we have the charge of 2 electron positive, 2 electron, yeah, positive. So 2 electron positive, but you do 1.60 10 raised to power minus 90 coulombs. When you do this, you get about 3.20 10 raised to minus 90 coulombs. So 3.20 10 raised to power minus 90 coulombs. Your delta V, you have to use this one now. So this goes like this over there. So it's a 400 volt. Your W you get about 1.3 to 10 raised to power minus 16 joules. So this is your word that people were required to move the alpha particle. So in this question, this ignore as we do with this one. This is the important. Sometimes you deal with that and you get the this one used and the answer was wrong. But you have to use that vertical one, not the horizontal one in that case. But when we do the other topic, we use that. So this is all work you have to do in this. So one other topic we have to cover is this, that motion between the charged plates, not the parallel plates, we have the charged plates. So in this we have the two cases. So the first case is we discuss now, and second case we discuss next lesson. So two cases of the motion of the charged parallel plates. Charged plates, electric field is the charged particle moving parallel to the electric field. Now we do the charged parallel particle with the electric field. And with that we do the initial wave perpendicular to the electric field. That initial wave perpendicular is the big topic we discuss next lesson. But now we will discuss the charged particle moving, which is parallel to the electric field. Now we involve the electric field in this again. So this means that the net force experienced by the charged particle between the plates will also be uniform. So when you do the net force, you know this is Ma. If the net force experienced by a charged parallel between the plates are uniform, so this means that Fe, this is electric force, is equal to Ma. So this means what? That Fe has the formula of this. Already this is on your data sheet, and this is equal to Ma. We use that condition too in that cases. When we do this questions, we use that cases too. That Fe is equal to F net. So one thing more, the conservation of energy stays that. As I told you, we do the conservation of energy in this too. So EKA plus EPA, this one. So this one is half mva square. As I told you, we do electric field with the potential energy. So that's the formula you have to use now. As I told you when we do the electric potential energy. Kinetic energy stays the same in that case. And this is it. That's the thing. And also in that case, your delta V is equal to VB minus VA. Because we're using the VB initially and the final. So it's VB minus VA now. So this thing, this thing, and this thing. You have to know now. These all not in your data sheet. So for this lesson, you have to know, and for the next lesson, we know more about later. So let's move on to one example for this. Last example for today's lesson. So we use energy laws in this too. An electron traveling with the speed of 3.80 to 10 raised to power 6 meter per second enters the right side of the parallel plane like it goes configuration. When it adds the configuration from the left side, when they adds it from there, the electron is slowed down to the speed of 1.27 into 10 raised to power 6 meter per second. Determine the potential difference between the plates and the strategy electric field. So, as this goes from positive to negative, so it goes from positive to negative. This means the electric field also goes to positive to negative. So this is the electric field because it goes from positive to the negative discharge. So this is your thing, and in this, initially this is the initial one. So this is the initial because from here the electron can enter, and from here the electron can go out. So this is your final one. So you want the potential energy difference between the plates. So you want basically what you want. So you want this VB you want. So that VB, which is your volt, so I don't like volt with this because we do also with speed, and your this VA, which is your volt, is 0. In that case, you have 0. And your VA, which is your speed, initially you have given, which is 3.80 10 raised to power 6 meter per second. And the final, when they exit through this, so this also is given to us, so which is 1.27 10 raised to power 6 meter per second. So we have this information and we want this VP. This we have to find. So this is also in like this formula. And with everything other thing we have, so we use that formula. So we have EKA plus EPA, EKB plus EPB. But initially your this one VA is 0, so this is cuts out. This is 0. So this is cuts out and you're left with this. So EKA is half MVA squared is equal to half MVB squared plus Q VB. That VB you have to find. So let's isolate this. So this is equal to half MVA squared minus half MVB squared. So from here you have VB, which is equal to this whole thing. So that's the thing you know. So now you have to put the things in if you want. So you can take half common and get this all conversion done. But I do it like this. So let's put the information in. So VB is equal to half. So in that case, you have to consider the mass of the electron. So mass of electron you can see from the data sheet where the particle section you have electron and we have a mass for this, which is about 9.11 into 10 raised to power minus 31 kg, which is VA. So VA is this starting point 4.80 into 10 raised to power 6 meter per second. square of this minus half, again the mass is same of the electron, and you have the final one to 1.27 you reduce to per 6 meter per second square of this. And the charge of electron, you all know that is 1 e, so minus 1 e, so its peak is 1.60 10 raised to minus 19 coulombs. So that's the whole big calculation you have to do in your calculator. And once you do this, you get about 36.517 volt. So this is your VB, and your VA is 0, this is volt. So you want delta D, which is dimension, and you have to find the potential difference between the plates. So which is VB minus VA. So this is equal to 36.517 volt minus 0 volt. You get potential difference about 36.5 volt. So that's all you have to mention. So that's all you have to do for this question. This is an easy type of question. You just use one formula like this. Sometimes you will use the potential difference formula to your electric field formula, which is delta V upon delta D. But this we will do in the practice questions when you do some extra things too. So that's all what you have to do when you do the charged parallel plates, the particle to the electric field. In that topic, we will do the initially perpendicular that concept. That concept is like something you have to know it this, and that's a tricky part, but we do. So that's all for this lesson. Let me say with EduVibe, learn smarter but not harder. Please like, share, and subscribe to my channel. If you have any questions, let me know in the comment section. So see you in the next lesson. Till then, stay connected with EduVibe.